While we can solve nonlinear systems by substitution, in some cases we can also solve them by elimination. The elimination process for nonlinear systems is really similar to the elimination process for linear systems. So let's go through the procedure and you'll probably find it familiar. Number one, choose a variable or a like term from both equations to eliminate. And then number two, multiply one or both equations by a non-zero constant to produce opposite coefficients for the term you choose to eliminate in each equation. So that one requires a little bit of thought, but our goal is to eliminate one term or one variable from both equations. Number three, add the equations together term by term. And this is going to yield a single equation and a single variable. Once we diagnose what type of equation it is, we can apply appropriate method to solve it. That's going to give us the answer for one variable. Then number five, back substitute the value or values obtained into either original equation and solve for the other variable. And then we have it. Our solution will be an ordered pair or ordered pairs, and we can always check that by substitution in the original equations. So here we go. Let's solve the systems on example 4 by elimination. We always want to express our solutions as ordered pairs, and to help us to visually understand what we found, we're going to graph both equations and identify the intersection points. So we have x squared plus y squared equals 16. That's a circle. And we have x squared minus 3y equals 16. That's a parabola. Notice the two equations have an x squared in common. So I'm going to eliminate x squared. In equation 1, the coefficient is positive 1, so I want it to have the opposite coefficient in equation 2. That is, I'm going to multiply all of the terms in equation 2 by negative 1. Now, there's no change for the first equation, so I'm going to copy it down as is. Then, multiplying through that second equation by negative 1, we get negative x squared plus 3y equals negative 16. Then I'm going to add the equations together term by term. Notice the x squared and the negative x squared cancel. That was our goal. We've eliminated the x squared from both equations. Moving on to the next spot, we have y squared plus 3y. Now those are not like terms, so I can't combine them. So I'm just going to write them side by side, y squared plus 3y. And on the right side, we have 16 plus negative 16 equals 0. So now we've whittled this down to a single equation in one variable. This is a quadratic equation in y, and we can solve it by factoring. Let's take out the GCF of y. That leaves behind y plus 3 equals 0, and so I have two possible y values, y equals 0 and y equals negative 3. So I want to find the x values that correspond to each one of those y values. So if y equals 0, then I'm going to use that first equation, x squared plus y squared equals 16 to solve for x. So let's plug 0 in for y, and we end up with x squared equals 16. Now be careful here. To solve for x, I need to take the square root of both sides. And when we apply the square root to both sides of the equation, as you know, we're going to get two solutions. So I get positive and negative 4. So that really means I'm dealing with two different points here. That is positive 4 corresponding to y equals 0 and negative 4 corresponding to y equals 0. So we had two ordered pair solutions that came from that one y value. But don't forget, we have another y value to consider. That is y equals negative 3. So again, I'm still going to use that first equation, x squared plus y squared equals 16 to find x. You could use the second equation if you preferred. So let's replace y with negative 3. This one's not going to be as pretty. We have x squared plus 9 equals 16. If we subtract 9 from both sides, that's going to give us x squared equals 7. And taking the square root of both sides, recognizing both the positive and the negative root, we have plus or minus square root of 7. So our ordered pair solutions then would be positive square root of 7 corresponding to y equals negative 3, and negative square root of 7 corresponding to y equals negative 3. So it looks like our curves are going to have 4 intersection points. Now, the square root of 7 is approximately 2.6. So when I locate this on the graph, I'm going to think of ordered pair 2.6, negative 3, and negative 2.6, negative 3. So let's attempt to graph both of these curves on the grid. The first equation is x squared plus y squared equals 16. That's a circle centered at 0, 0 with a radius of square root of 16 or 4. So from the center 0, 0, I'm going to measure 4 units in the 4 cardinal directions, up, down, left, and right, and then connect those dots with a circle. And that's our equation, x squared plus y squared equals 16. Now, the second equation there is a parabola. We could rearrange it and isolate y to make it a little bit easier to work with. That is, let's take our x squared term and subtract it to the other side. And then let's divide all of our terms by negative 3. So that's going to give me 1/3 x squared minus 16/3. So thinking about transformations, this is our ordinary parent function, our parabola. It's multiplied by 1/3, so it's going to be a little bit wider than normal. And also notice it's been translated down 16/3 units. So at least we could say our vertex is at 0, negative 16/3, or let's think of that as negative 5 1/3. So my vertex will be approximately right here. Now, as far as finding other points on the graph, this is kind of a messy parabola, but I discovered that the x-intercepts are pretty user-friendly. So let's complete our parabola by plotting the x-intercepts. Remember, to find an x-intercept, we set y equal to 0. So I'm going to go back over here just for some workspace, and I'm going to set y equal to 0. And notice that gives us this equation, x squared equals 16. The solutions to that equation would be plus or minus 4. So the x-intercepts of that parabola, 4, 0, and negative 4, 0. And notice that lands right on our circle. Okay, so we know it's a parabola. I'm finding some points to plot, and I'm going to do my best to connect the dots there. I think I can do a better job on this left side. There we go. So that would be the equation, x squared minus 3y equals 16. So let's test the accuracy of our graph. We came up with 4 intersection points, 4, 0, and negative 4, 0. Those are pretty clear right here. So one solution, one intersection point is negative 4, 0, and that one clearly is 4, 0. The other two, we have negative 2.6, negative 3. About right here. I'm going to call that negative square root of 7, negative 3. And the other one, 2.6, negative 3. Pretty close, not exact, but we'll trust the algebra and call that square root of 7, negative 3. So we can see that the circle and the parabola intersect in 4 points. It's difficult to read them accurately off the graph, but our algebra is reliable, so we know the algebra gives us the exact intersection points of those curves. Okay, let's try one more. We want to solve by elimination. In this case, we have x cubed plus y equals 0 and 2x squared plus y equals 0. Both of our equations contain a y, so let's eliminate y. So I'm not going to make any changes to the first equation, but I want to multiply all of the terms in that second equation by negative 1. That's going to give me negative 2x squared minus y equals 0. So our first two terms are not like terms, so I can't combine them. We'll just express it as x cubed minus 2x squared. But we have successfully eliminated our y values, and we have a 0 over here on the right side. So this is a degree 3 polynomial equation. It's equal to 0, so we can easily solve this by factoring. Our greatest common factor is x squared, and that leaves behind x minus 2. If we set x squared equal to 0 and take the square root of both sides, we'll get x equals 0. And from our second factor there, the 0 is 2. So let's find the corresponding y values for these x values. When x is equal to 0, I'm just going to use that first equation, but remember you can use either one, to plug 0 in for x and then solve for y. Clearly we're going to get y equals 0. So one intersection point of our two curves will be the origin 0, 0. When x equals 2, again using that first equation, x cubed plus y equals 0, I'm going to replace x with 2 and solve for y. It looks like y equals negative 8. So when x is 2, y is equal to negative 8. Let's see if these appear on the graph. So our first equation is x cubed plus y equals 0. Let's rewrite that as y equals negative x cubed. I'm just subtracting x cubed from both sides. Then we can see that's our parent function x cubed reflected across the x-axis. So that graph is going to pass through the origin, ordered pair 1, negative 1, and 2, negative 8. It's going to pass through ordered pair negative 1, 1, and negative 2, 8. Might be a good opportunity to go back and review the details of those parent functions. So there's our first equation, y equals negative x cubed. Or if we want to express it in its original form, we can call it x cubed plus y equals 0. Our second equation there is an ordinary parabola, 2x squared plus y equals 0. Let's rewrite that as y equals negative 2x squared. Just subtract 2x squared from both sides. So we can think of this as our ordinary parent function parabola that's been reflected across the x-axis and stretched by a factor of 2. So it's going to pass through the origin, 0, 0. It's going to contain ordered pair negative 1, negative 2, and 1, negative 2, negative 2, negative 8, and 2, and 8. You can certainly check that with your calculator, or you can go through the details of the transformations. So that would be 2x squared plus y equals 0. All right, let's see how we did on our intersection points. Clearly the two curves pass through the origin, so we can see intersection point 0, 0, and the other one, pretty easy to find as well, 2 and negative 8. So our algebra gave us the exact intersection points, and the graph came out pretty good on that one. And remember, you can also certainly check those with your calculator. So now you can solve a nonlinear system both by substitution and elimination.